A group of physicists working within a government laboratory just managed to make time flow backward inside a quantum system. This isn't a figure of speech, and it isn't a simulation either. The quantum processes within their experiment actually behaved as if time had reversed its direction, and they achieved this using only measurements and feedback. Classical physics offers no explanation for this. Classical physics insists this simply cannot occur. In February 2026, a team of researchers at Los Alamos National Laboratory, working together with collaborators from the National Institute of Standards and Technology and the University of Maryland, published a paper in Physical Review Tense, one of the most highly regarded physics journals in existence. The paper's title is both blunt and unnerving: Reshaping the Quantum Arrow of Time. The physicist leading the study is Luis Pedro Garcia Pintos. Cutting through the technical language, here's the discovery. Through carefully engineered control methods, a quantum system can be made to act as if time were running in reverse. Not delayed, not frozen, actually reversed. Like and subscribe, because the physics history underlying this claim only gets stranger the deeper you dig into it. Every single experience of your life confirms one unshakable truth about time. It only moves in one direction. A mug falls off a table and smashes into pieces. It doesn't put itself back together and leap up onto the table again. A flame reduces wood to ash. That ash never spontaneously compresses itself back into wood and unburns. Your body grows older. It doesn't grow younger. Every physical event you've ever witnessed backs up the idea that time has a direction, an arrow pointing endlessly forward from past into future. That arrow is so consistent, so thoroughly woven into every second of human life, that most people have never really stopped to question whether it's actually fundamental. It seems like the most self-evident feature of existence imaginable. It's even built into the way we speak. We talk about before and after, cause and effect, memory versus anticipation, concepts that all assume a single direction of time and would collapse into nonsense otherwise. The forward march of time is so ingrained in human experience that, for most of physics history until fairly recently, scientists simply took it for granted rather than treating it as something that needed explaining. Physicists do have a technical name for this directionality. They refer to it as the thermodynamic arrow of time, and it stems from a concept known as entropy, which, put simply, measures disorder. The second law of thermodynamics, among the most foundational laws in physics, states that entropy inside a closed system either holds steady or grows over time. Disorder doesn't spontaneously turn back into order on its own. Broken mugs don't reassemble. Burnt wood doesn't unburn. As a consequence, time flows in a single direction, and every observation you've ever made supports that. This particular law has been put through more testing than nearly any other principle in scientific history, across every imaginable scale of matter, from the tiniest subatomic particles up to entire galaxy clusters, across temperature extremes from nearly absolute zero to millions of degrees, and through every experiment physicists have devised specifically to try to break it. At the everyday macroscopic level, no exception has ever turned up. The second law isn't a rough approximation. It's not something that merely holds true most of the time. It stands as one of the closest things to an absolute truth that science has ever managed to produce. Now here's the part where quantum physics throws a wrench into everything. Down at the microscopic level, the core equations that govern how particles move and interact show no actual preference for one direction of time over the other. Quantum mechanics, in a technical sense, is time symmetric. If you took the equations describing how a quantum particle behaves and swapped time for its negative equivalent, those equations would remain just as valid. Both forward and backward time are mathematically permitted. The arrow of time you experience in daily life doesn't originate from this underlying physics at all. Instead, researchers believe, it emerges from the way quantum systems interact with their surroundings, and in particular from the act of measurement itself. This is one of the deepest and most enduring puzzles in all of theoretical physics, sometimes referred to as the problem of the arrow of time. Erwin Schrödinger was aware of it. Ludwig Boltzmann, the scientist who built the mathematical foundation of entropy back in the 19th century, wrestled with it so intensely that it may have played a role in his psychological decline and eventual death. The equations describing microscopic physics permit a shattered mug to reassemble just as easily as they permit it shattering in the first place. The traditional explanation for why it never actually happens comes down to probability. The number of ways a mug can end up shattered massively outweighs the single precise arrangement of atoms required to send every fragment flying back into an intact cup. So the broken configuration is astronomically more probable than the whole one. Under this framework, entropy is essentially just a tally of possible arrangements. Sit with that for a second. The reason time seems to move forward throughout your life might not be some fixed law of the universe at all. It could instead be a byproduct of how quantum systems behave when they're being watched. Like and subscribe, because this exact idea has lingered at the fringes of physics for decades, and this new Los Alamos paper has just found a way to experimentally manipulate it. In quantum physics, taking a measurement isn't a neutral, hands-off act. The moment you observe a quantum particle, that observation randomly alters its state. Researchers think this random shift is one of the key mechanisms through which the arrow of time gets stamped onto a quantum system. Each measurement nudges the system further forward in time, in a way that's probabilistic and irreversible. The more measurements you take, the more solidly the arrow of time becomes locked into the system's behavior. This measurement-triggered arrow of time is one of the strangest, least talked about corners of quantum theory. Classical physicists could, in theory, watch a system without disturbing it, or at least without disturbing it in a way that matters thermodynamically. Quantum mechanics rules that out entirely. Every act of observation, however gentle, disrupts the quantum system in a way that's random and irreversible, and that disruption feeds directly into the system's entropy. This is exactly why quantum systems are so tricky to keep in their useful computational states. Observation carries a thermodynamic price tag in quantum physics that simply doesn't exist in the classical world, and every functioning quantum computer on the planet is battling that effect constantly, moment to moment. The Los Alamos researchers approached the problem from an entirely different angle. What if, instead of just measuring a quantum system, you paired those measurements with precisely tailored feedback? What if the information gathered from each measurement was used to apply a specific correction, an engineered control field called a Hamiltonian, that canceled out the forward time push caused by measurement and swapped in a backward time trajectory instead? That's precisely what they built. The team constructed a control Hamiltonian, a mathematical instrument that precisely mimics the random, evolving paths a monitored quantum system takes. Once folded into a feedback loop, this Hamiltonian can accomplish three things that had never before been achieved in a controlled experimental setting. It can neutralize the arrow of time that would normally arise from measurement, leaving the system in a kind of temporal limbo. It can amplify the arrow of time, pushing the system's behavior even more strongly forward. Or it can flip the arrow altogether, producing quantum trajectories that appear, by every measurable standard, to be running backward through time. The Hamiltonian itself isn't a physical thing. It's a mathematical representation of the energy relationships within a quantum system, translated into a precisely timed sequence of pulses and fields applied to the qubits. Picture it as sheet music the quantum system reads, where every note corresponds to a specific electromagnetic pulse delivered at a specific moment, and the whole composition is engineered to force the system's statistical behavior to run against its natural grain. The Los Alamos group didn't stop at showing this was theoretically achievable. They laid out a full, generalized construction method, essentially a blueprint that other research teams can now adopt for their own quantum hardware, rather than having to reinvent the underlying math from the ground up. But that isn't even the most jarring part of what they created. To showcase the power of this technique, the team also built what they call a quantum version of Maxwell's demon. Maxwell's demon ranks among the most famous thought experiments in the entire history of physics, first proposed by Scottish physicist James Clerk Maxwell back in 1867. In the original version, an imaginary demon stands guard at a tiny door separating two chambers of gas. It watches individual particles zip by and selectively opens and shuts the door, letting the fast-moving particles into one chamber and the slower ones into the other, effectively separating hot from cold without seeming to expend any energy at all. In doing this, the demon appears to lower entropy, breaking the second law of thermodynamics by making disorder spontaneously arrange itself into order. For more than 150 years, physicists debated why this scheme couldn't actually function in reality. The answer, eventually nailed down rigorously by Rolf Landauer in 1961, and later sharpened further by Charles Bennett, is that the demon's process of collecting and holding information about the particles carries its own thermodynamic price. Once you fully account for that cost, entropy doesn't actually go down after all. The demon isn't beating the second law, it's just shifting the disorder somewhere harder to see. Every scrap of information the demon retains about which particle went where comes with a minimum thermodynamic cost, now known as the Landauer limit, and wiping that information at the end of the process is where the entropy bill ultimately comes due. This resolution is elegant, but it carries a striking hidden consequence. If information itself carries a thermodynamic cost, then information is, in a real sense, a physical resource, just as tangible and exchangeable as energy or momentum. The Los Alamos team built their work directly on top of this insight. Their quantum daemon takes information collected from measuring the state of a quantum system, combined with the results of the feedback process, and uses it to produce behavior that reverses the system's natural arrow of time. It treats information not merely as a byproduct of measurement, but as a genuine thermodynamic resource, a form of energy capable of performing real physical work. To demonstrate this, the team built a continuous measurement engine, a device that pulls usable energy straight out of the act of taking quantum measurements, something no classical system is capable of, since in classical physics, measuring an object doesn't alter it in any thermodynamically significant way. Like and subscribe, because a device that draws energy from the very act of observation is one of the most conceptually alien ideas engineering has ever produced. Now, it's worth understanding the distinction that really matters here, because claims that scientists have, quote, run time backward have popped up in various forms across several different experiments over the years, and almost every one of them has needed a very specific caveat attached. The 2019 Argonne National Laboratory experiment, the 2023 University of Vienna photon experiment, and the 2025 results out of the University of Surrey all demonstrated some version of quantum time reversal, but each was limited to a single particle or photon, and each depended on already knowing the system's exact prior state ahead of time. You can't genuinely unknow what you've already observed. You can't run time backward inside a system without that prior knowledge functioning as a kind of built-in shortcut in the calculation. The Los Alamos paper represents a real advance beyond those earlier results specifically on this point. Its feedback-based control protocol works on quantum trajectories, the statistical paths a quantum system traces as it evolves, rather than depending on complete knowledge of a specific starting state. Garcia Pintos and his co-researchers set out to design a technique broad enough to apply across many different quantum systems and processes, not a one-off trick tailored to a single special case. The end result is a protocol far closer to something that could genuinely run inside an actual quantum computer than anything previous demonstrations of apparent time reversal had achieved. The University of Surrey study, published in February 2025 under the title Physicists Uncover Evidence of Two Arrows of Time Emerging from the Quantum Realm, tackled this same territory from a different mathematical direction, uncovering evidence within quantum theory itself, suggesting time might not run uniformly in one direction, even within a single quantum system. That was a theoretical finding, a mathematical discovery rather than an engineered demonstration. The Los Alamos paper pushed decisively past uncovering and into building, offering the first complete, general-purpose engineering protocol for putting that theoretical freedom to practical use. The team specifically noted their next step is to actually implement these Hamiltonian-based measurement protocols on superconducting qubit systems, the same hardware platform used by IBM, Google, and other major players in quantum computing. Superconducting qubits allow for rapid feedback and highly efficient detection, precisely the qualities needed to prove that this theoretical framework can generate real, measurable backward time behavior on genuine quantum hardware, not just inside mathematical models. Now here's where things get genuinely unsettling for anyone assuming this was purely academic research. The practical uses the paper explicitly points toward aren't decades away. Quantum state preparation, the ability to precisely set a qubit system into a desired starting configuration before running a computation, remains one of the central unsolved engineering challenges in modern quantum computing. Error correction, the task of fixing mistakes mid-computation without wrecking the whole calculation, is the other major hurdle. Both of these problems trace back to a shared culprit, entropy. Disorder building up inside a quantum system corrupts computations, scrambles qubit states, and forces computers to burn enormous resources on error detection rather than actual processing. A control protocol capable of reshaping or flipping the arrow of time inside a quantum system is, in practical terms, a tool for fighting entropy from within an active computation. Not by isolating qubits more effectively from noise, which is the approach the industry mostly relies on today, but by actively steering the system's trajectory backward against the natural pull of entropy, using nothing more than measurement and feedback. That's a fundamentally different engineering strategy for tackling the same problem, one that could eventually work alongside, or even partly replace, some of the most resource-heavy error correction schemes currently being developed. The resource demands of current quantum error correction are almost outrageous. Most methods need somewhere between 10 and 1,000 physical qubits just to keep a single reliable logical qubit stable throughout a computation, because individual physical qubits are so fragile and error-prone that only through massive redundancy can their information be trusted. A feedback-driven protocol that can actively reverse entropy buildup inside a qubit system, rather than just cleaning up errors after they've already happened, could, in principle, dramatically shift that ratio, cutting down the overhead needed to sustain a reliable logical qubit and bringing fault-tolerant quantum computing within reach at far smaller physical qubit counts than today's roadmaps assume. This isn't guaranteed. The Los Alamos protocol hasn't yet been tested on real hardware for this exact purpose, but the mathematical groundwork now exists, and it points toward exactly the direction the quantum computing industry has been chasing. Consider also the energy harvesting angle, which the paper's authors describe as one of the most immediate practical uses of this work. Classical computers generate massive amounts of waste heat, a direct byproduct of the second law of thermodynamics. Every irreversible computation generates entropy, and that entropy has to be released as heat somewhere. Data centers worldwide burn through hundreds of terawatt-hours of electricity annually, and a large chunk of that ends up as heat that does no computational work at all. A quantum system able to harvest energy from the measurement process itself, treating information as a thermodynamic resource rather than throwing it away, would represent a fundamentally different relationship between computation and energy. One where some of computing's thermodynamic cost could actually be recycled into useful work. A fully realized, scaled-up version of a device like this would essentially function as a quantum battery, charged by observation itself. Every time the system's state gets measured, instead of that measurement irreversibly pushing the quantum system into a higher entropy state and releasing heat as a side effect, the feedback-driven control protocol channels that thermodynamic push into usable work, storing or applying the energy that would otherwise be lost. That concept is still in its early, largely theoretical, small-scale experimental phase, but it marks a genuine break from the basic assumption baked into every computer ever built, that computation must inevitably generate entropy, and with it, heat. Like and subscribe, because this idea sits at the crossroads of quantum physics, computer engineering, and energy policy in a way that almost nobody outside the research world has really started grappling with yet. But here's the honest limit of what this experiment actually accomplishes, and staying clear-eyed about that boundary matters more than hyping up any single discovery beyond what it truly shows. The Los Alamos team did not reverse time at the macroscopic scale. They did not send information into the past. They did not open a channel for cause and effect to run in reverse. What they built is a precision engineering tool for manipulating the statistical behavior of quantum trajectories, making them statistically match backward time dynamics within a closed quantum system over brief timescales under tightly controlled laboratory conditions. It's worth pausing on exactly what these limitations rule out, because they rule out precisely the things popular coverage of this story is most eager to claim. You cannot use this technique to receive information from the future. You cannot use it to undo some event out in the external macroscopic world. You cannot use it to make a shattered coffee mug put itself back together, because a broken mug isn't a quantum system under controlled measurement and feedback. This technique functions in the deeply microscopic domain, within the quantum realm, on systems made up of a handful of qubits, under conditions demanding extraordinary experimental precision, and it collapses entirely the instant the system is exposed to any meaningful outside interference. A shattered coffee mug won't reassemble on its own. Your body won't grow younger. The second law of thermodynamics stands exactly as firm as it did before this paper came out. What has changed is that physicists now possess a working, general-purpose protocol for reaching into the strange, time-symmetric microscopic world that the second law arises from, and bending that world's behavior in a controlled, repeatable, technologically useful way. This isn't time travel. It's arguably something more interesting than that. Proof that the arrow of time isn't a wall, but a dial, at least at the quantum scale, and that researchers have now built the first general-purpose tool capable of turning it. The path forward from here is clear, even if it's a long one. Superconducting qubit experiments will need to put this protocol to the test on real hardware, not just in theory. Error correction researchers will need to determine whether feedback-driven time reversal can meaningfully cut down qubit overhead during actual computations. Energy physicists will need to figure out whether measurement engines of this kind can generate thermodynamic gains substantial enough to matter at real engineering scales. Each of these is a legitimate open research question, not a certain outcome. But the mathematical framework now exists. It's been peer-reviewed in one of the most rigorous physics journals on the planet, and it points in a direction the entire quantum computing field is watching closely. At the human scale, the universe keeps moving forward through time without asking anyone's permission. At the quantum scale, it turns out, the universe has been quietly indifferent to that direction for billions of years. We simply took a very long time to notice we could ask it to look the other way.